So I'll share all of those with you as an announcement. All right, so let's get started. We already started discussing chronic penny model, and I told you that this is never going to be part of any exam or any quiz. You're not going to be challenged with the concepts that I'm going to cover here in chronic penny model. I still decided to cover this because I hope, even if you remember bits and pieces of these concepts, in the next lecture or so, the lectures that are coming up, it will be easy for you to relate to the origin of band diagram. So that's where we are headed, band diagram. Band diagrams are kind of like the crown jewels of semiconductor industry. That's, band diagrams are the tools that we use to basically try to understand devices or describe how devices work. It's that impactful. All right, so in chronic penny model, we started with a model of an atom, a potential distribution in an atom, and then we noticed that the resultant potential distribution is similar to a periodic potential, kind of like a rectangular barrier, but obviously it's an approximation of the actual potential. And we notice that it has periodicity because it will keep repeating itself over and over again. So using that periodic concept, we decided to use Bloch theorem and simplified the work function a little bit. We tried to write Schrodinger's equation for two regions because it's periodic. Once you do it for these two regions, it will be basically shared everywhere. So that's what we are doing. We were trying to describe the activities of electron using for some reason it's not letting me. Give me a second. Okay. All right, give me a second. Something's wrong with this PowerPoint. I think PowerPoint froze for some reason. Let's see if it works now. Okay, it's good. So yeah, so we approximated this potential distribution as square or rectangular shaped, and we were trying to find ways to describe the behavior of electrons in two regions, region 1 and region 2. So we wrote down Schrodinger's equation for these two sections, which I didn't even try to explain. I just went over quickly to this slide where we found a mathematical expression, which is not a solution. And by the way, all of these are written. No, this is not even a solution to Schrodinger's equation. It's not even a solution. This is just a condition that we need to meet to even claim that there is a solution. Okay, so just remember that. So we are going to deal with this condition, and obviously we'll have to realize this, otherwise we cannot explain the behavior of electron anywhere inside the crystal. So with this condition, we just took a little bit of a side channel and considered a special case. What was that special case? Special case was free electron. What if we have a free electron? We were just curious, and I told you we'll get back to this, right? So if you have a free electron, this quantity, which was dubbed as P prime, would be 0 because the potential is 0 for free electron. Potential, there is no potential barrier. And then basically we ended up getting alpha equals K, which we replaced in this equation and eventually found a relationship between K and E. Just to remind you, E is energy of the particle. In this case, it's the electron. And K was the quantity called wave number that we encountered before in one other quantum mechanical calculation. So interestingly, this is a very simple equation, and if you plot it, it looks like a parabola. That's what I wanted to highlight, and I told you that we'll get back to this graph a little bit later. This is an energy versus K diagram. So get used to the term EK diagram. EK diagram. So oftentimes in semiconductor industry, when the engineers talk to each other, can you draw the EK diagram for this? Let's discuss this, blah, blah, blah. So they use the EK diagram to decide which material is good for a particular application and which are not. So it's that ubiquitous, okay? We are just beginning to see that this diagram exists, okay? It's kind of like learning that periodic table exists for the first time, right? Without periodic table, how can you talk to without knowing what periodic table is, how can you talk to a chemist, right? So similar to that, EK diagrams are the basis of conversation. Anyways, moving to the next one. It's a very nice, simple EK diagram that you could describe as a pure parabola for a free electron, remember. Okay, now, this is where we kind of stopped in the last class. So it's the perfect place for us to start again. So please pay attention. This was the condition that needs to, man, for some reason, oh yeah, for some reason, I guess, is it the pen or is it PowerPoint that's messing things up? Yeah, some things. Sorry, please bear with me a second. I will try one more time to restart PowerPoint, and then we'll see if that helps. Start it from scratch. Okay, I hope this time. Oh, not you. Because I need the pen. But I hope we are lucky. No, we're not lucky. My goodness. All right. I don't know what's going on with the pen, and it has full charge. So let's try to visualize this as the best as we can without the pen for the time being. And then if for some reason it's completely intangible, I'll try to draw something on the whiteboard for today. I have a backup plan, but obviously that's at home. All right. Anyways, so just take a look at, can I at least turn on the pointer? Maybe. Yeah, I guess so. Oh, yeah. Oh, never mind. I could just draw with my finger. So good. Never tried that one before. I mean, why would I, right? Got iPad simply because of the pen, and then the pen doesn't work. Anyways, so this is the condition that needs to work or be satisfied if we are to get a solution. Now, take a look at the left-hand side and the right-hand side separately. On the left-hand side, we have two quantities, but the right-hand side is simpler. So let's start with the right-hand side, which is a cos function, cos of anything. So cos of anything could have a maximum value of 1 and a minimum value of -1, as I told you. So let's just draw two lines here, as 1 and 2. So the top one representing +1, the one on the bottom representing -1. So we just know that there is a limit to the right-hand side. The right-hand side can never go up to 1, go below -1. So that's what we know. Let's take a look at the left-hand side. Left-hand side has two quantities, one involving sine, the other one involving cosine. So if you draw the one involving sine, as you see marked here with different color, you get a shape like this. If you plot it in MATLAB, you'll get a shape like this. It's pure math, nothing else, and geometry. Just plot it, you get a sigmoid shape like this. Plot the cos function, you know how cos functions look like. Fine, very good. And it is super simple because you see on the x-axis you have alpha a, which is this quantity. On the y-axis, you are basically plotting the entire value. Same applies here, alpha a and the cos alpha a. And then you basically have them added together. So just add these two functions. And when you add them, you get a shape like this. Right? Super simple. So you could just do it on MATLAB. Plot one, plot the other, add them up, you get this interesting shape. Now, that's where our business begins. We already know, oh, by the way, the left-hand side should be equal to the right-hand side, obviously, as you know. But we also know that the right-hand side cannot go above 1 and -1. But the left-hand side apparently could go up and down. It could cross that limit. So to satisfy this condition, we have to make sure that we only stay within this region. Do you see that, folks? Does that make sense? To make sure left-hand side equals right-hand side, we could only stay within a certain region. We don't care about the other ones. So other ones are not valid. So now this shaded areas, the blue shaded areas that you see here, do you see what that represents now? These are the zones of that complex shape, kind of sigmoidal shape, that is within -1 and 1. Take a look at it. Can you guys see that? Folks behind, can you see that? Okay. I know it's a little bit on the other side. Okay, let me see if I can. Man, technology has its challenges, Okay, now it's letting me go to the other slide. So I was trying to zoom in so that you could see. Can you see it now? So my point is, within +1 and -1, you have certain zones of the graph that will potentially satisfy the left-hand side equals right-hand side situation, but the others will not. So only these sections that are marked blue are valid. The other ones are not. Does that make sense to you guys? We all agree on this, right? So what we are going to do is basically just take only the shaded regions and discard everything else. Notice one more thing. In the x-axis, you have alpha A. I have to do it every time. Okay, so on the x-axis, you have alpha A, but on the right-hand side, you had Ka. Do you notice that? For the cos on the right-hand side, you had Ka. But for the quantities on the left-hand side, you have alpha A. Right? So there is a way to relate K and A together, which we did in the last slide. You might have noticed that. So we basically convert alpha A into Ka, and let me just get to the next slide and show you what we get. So we get to the next slide. All right. So instead of alpha A, we are going to just plot it in terms of K in the x-axis. You see that this is just K. We got rid of A entirely, and the A, instead of pi, 2 pi, we started writing it as pi over A, 2 pi over A, because we converted Ka to just K. Simple axis transformation. What's the reasoning? Because we are going after, notice, what is that? EK diagram. We're going after energy versus wave number diagram. Okay? EK diagram. But again, just to be, just to quickly get to the point, you notice that the diagram looks like a disjoint graph. So you have something here, you have something else, and there are regions where there is nothing. Can anybody realize why there is nothing in between? If you remember the previous slide, right? There are certain zones that were allowable, certain other zones that were not. So if I go to the next slide, this slide, and remember this graph, some of this were valid, others were not. So if we only take the valid zones and plot them, there will be some discontinuity, don't you think? I'm not showing you the conversion, the axis how we are getting from alpha A to Ka and then just K. There are some axis conversions involved. That's why the graph shifted from horizontal to vertical direction. So basically we moved the variables and whatnot. But the point is, simply because of this valid and invalid region, simply because of the existence of valid and invalid regions, we get a discontinuity in the overall EK diagram. Let me show you here. Do you see that there is a discontinuity? There are steps, like you have a zone which is really nice and streamlined, and there is a discontinuity, and there is another zone which is allowed, and then there is another discontinuity, and the source of discontinuity is coming from you getting out of +1 and -1 in the previous slide. So they're related. So I obviously skipped several lines in between these two figures, but I hope you can somehow relate to it. Can you? Okay. Now, more important point is, how many of you remember that? Let's go to the next slide. Cos theta and cos 2 pi plus theta is basically the same. You know that? If you basically shift something by 2 pi to the left or right, if you shift cos by 2 pi, it's basically going to give you the same thing. So engineers decided to simplify the representation of these diagrams because they can just go on, like they can be wide, really wide, right? Just to simplify, they decided to shift them to left by 2 pi because that's going to keep the value exactly the same. So imagine, take this graph and shift it by 2 pi. You get this graph. You see that? Notice as I draw. Or take this graph and shift it by 2 pi, get this one. So similarly, so shift everything by 2 pi and try to bring them closer to the center. As if you're folding this thing. Like it was like too wide, you're just folding it for your comfort. Because otherwise, I mean, oh man, it's a huge wide diagram to draw. Let's not do that. So we could easily bring everything from all the corners to the center. We're going to do that. And this is the final result. So basically by shifting and folding everything, you get something known as the reduced EK diagram. Reduced EK diagram. Okay. It's kind of like if you go to semiconductor company, the nerds will talk about, hey, how is your reduced EK diagram looks like? This is basically super simple stuff. EK, fold it to reduce the size, and you get a reduced EK diagram. So, and I'm getting into what this EK diagram can do for you. And the last slide of this lecture will show you the power of this EK diagram and how they are like literally game changers. So not too long, like couple of slides left. Are you guys still with me so far? So my end or punchline, I should say, is to get to this EK diagram. And now I could potentially take a moment and try to relate this to EK diagram of a free electron. How many of you remember? We just discussed the EK diagram of a free electron. It looks like a parabola. Was there any discontinuity in there? No, it was like really nice, sweet, smooth parabola. So just draw it on top of it. For a free electron, it could have been like a really nice, smooth parabola, but not anymore. For this case, it's kind of complex. There are different shapes, there are discontinuity, there are forbidden regions and allowed regions. So it's a little bit more complex. Why? What changed? In a crystal, electrons are stuck. So there are regions of allowed energy and forbidden energy and things like that. But if an electron becomes free, there is a continuous energy distribution, basically. But free electron is like a hypothetical concept. It's always stuck somewhere. Anyways, so let's move to the next slide. I think it's a problem with PowerPoint, not really. Maybe an update messed things up, but not really the pen, because every time I try to get to the next slide, I'll have to end the presentation and go to the next slide. All right. So we are going to start looking at this. You see, there is no begin and end here in this slide because we have gone past the section that doesn't matter to you. If you don't care about it, just ignore it, forget it. Anyways, I skipped a lot of steps. In case you're interested, that's why the book was referenced. So in case you're interested and you want to have a conversation with me, please feel free now or in future. Maybe when you go to grad school, you might want to dig deeper into it. Sure, right? But otherwise, don't bother too much. You don't have to worry about it. But from this slide onwards, we do have to care because now we're getting into engineering. So after we understand that there are bands. Oh, I forgot to tell you about the bands as well. This is the most important take home here. So these zones that you see that are allowed, and there are zones that are not allowed, like maybe this ones. The zones that are allowed, where you see some sort of graph, that's called, some sort of band of energy. Band is just another name for range, like a range of energy that is allowed. And we call it band. And wherever you don't have anything, you have a discontinuity, that's called forbidden band. Okay. So for any material, semiconductor or not, you'll always have this kind of a EK diagram, especially for single crystal material, by the way. I'm not talking about any other like amorphous or other things, because it's really difficult to do anything with amorphous material. Remember the very first slide of the very first lecture, I showed you 3 different kinds of materials: single crystal, polycrystalline, amorphous. Can anybody tell me the analysis that we just saw, chronic penny model based calculation, what type of material does it apply to? Please go ahead, make a mistake, just go ahead, tell me. Speak up. Is it amorphous? Is it single crystal? What was single crystal material? You had really nice, well-structured distribution of atoms everywhere. It follows a rule. Did we start with a structure that follows a specific rule or no? Remember, why is it periodic potential? Why is it always the same? Because it is single crystal. Am I making sense, folks? Can you relate this diagram? Let me just go back to this diagram again for a second. So can these sections that you see here, these are atoms. Oh, I thought I was drawing. Atom, atom, atom. That's why it's kind of like a well, potential well, because in atom, electrons are stuck. Electrons are stuck in atom. You see that? Am I making sense? So whenever there is an atom, it's kind of like a well that the electrons can fall into and get stuck in an atom. So all of these atoms are really nicely distributed in a single crystal. So whatever we are doing here, these are all for single crystal. Remember that. That's one thing. Okay. That's why I told you single crystal materials are the most important materials for semiconductor industry, because we can predict them. We could do some math. But if it were like polycrystalline, what will change? Can anybody tell me? Will it be? Yes, the pattern will be random, totally random. I mean, how can you do the math? Here, we could just deal with two Schrodinger's equation in region 1 and region 2 and describe the entire system. So simple. But there, like if it were polycrystalline or amorphous per se, we had no idea, right? It's very difficult to predict using this type of simple method. I'm not saying it's impossible, but it's very difficult to do. Okay, so it's not going to be as this is simple compared to the standard that we deal with. Number two, we are assuming that electrons are not correlated. This is a very important distinction. Remember that. I mean, if you read through the text here or in the textbook, you will see it will say in one sentence, which I didn't understand as an undergrad. What does it mean? The electrons are not correlated, meaning one electron is its own entity. It is dealing with the barriers just by itself. It's not getting any help or any opposition by any other electrons. But in practice, electrons can be correlated. One electron can interact with another electron. So we are ignoring electron-electron correlation. You are never seeing how one electron behaves with the other one, basically ignoring the fact. I expected that somebody would ask, hey, wouldn't there be electron-electron correlation? Like, all we are seeing here is electron barrier interaction. So electron hitting a barrier as if there is no one else. It's hitting a barrier, doing its job, tunneling whenever it feels like, whatever, just the electron by itself. But what if there are other electrons? Then there will be interaction, and this will be a more complex math. Am I making sense, folks? All right. Do we care about materials that have correlated electrons? At some point, we could live without considering them. But now, in modern day electronics, we're dealing with them on a regular basis. And I will just give you one example so that you can look up on Google if you want to. A superconductor. How many of you have heard about superconductor? Many of you. Okay, it's good. I'm happy to know that. Do you know that there is a field of electronics that exists called superconducting electronics? Superconductors are correlated materials. So basically electrons, the reason why superconductors are superconductors is because electrons get correlated. They basically form a pair. Imagine how crazy it is. Two electrons forming a pair and work like basically moving together. Instead of one electron moving, you have pairs of electrons moving. It's called Cooper pair. And I don't want to take too much tangent, but the point is those crazy kind of things occur when the electrons get correlated. Why didn't you wonder? Electrons are all negatively charged. Two negative charges should repel each other and move away. Hey, I hate you, right? But no, two electrons forming pair and moving together. And it's not just two electrons. All the electrons are forming pairs in a superconductor. And they're moving like pairs, like couples, essentially. So that's what correlated electronics can do, make or give rise to extraordinary properties. My PhD was related to a type of material called correlated oxides. Vanadium oxide, niobium oxide, this kind of materials, they have correlated electronics, and that gives rise to a property that in certain conditions, the material behave like a metal. Or you could make it behave like an insulator, like really good insulator, really good metal. Just imagine a material at will can behave, I'm a metal today. I'm an insulator today. Obviously, it's not as easy as I'm saying, but this type of interesting, complicated situation can arise because of correlation. So I hope it makes sense to you how simple this situation was. It was uncorrelated electrons, single crystal, so everything was idealized. And also the final punch is 1D, one-dimensional. The materials, even the single crystals are three-dimensional. So you're ignoring a lot of things here. Even with all those, assumptions and whatnot, eventually we arrived at one final conclusion, which is that you have allowed bands and you have regions of energy that are allowed and you have regions of energy that are forbidden. Now, you have many, many bands, right? And it's not the end, by the way. If you keep plotting, there will be bands on top of it as well. There is one minimum energy band, and then it will just keep going. Even for hydrogen, you have a lot of bands. They come mathematically. But in practice, hydrogen will probably never use those bands. It will just stay with one band. But in theory, if you provide enough energy to the electrons can go from one band to the other, and to the other, and to the other. But you will have to provide insane amount of energy to even access second or third or fourth band. So they never really come into practice. Okay. For most materials, we typically deal with a band beyond which the electrons are almost like free electrons. I mean, they don't no longer belong to the material. Okay. So we don't care about all the bands that are underneath. We just care about the one that is at the edge. And we don't care about all the other bands that's above it. We just ignore all of them. Just keep the one that marks the boundary between an electron being committed to an atom and an electron being free. I don't care about this atom. Making sense? Are you guys still with me? Don't give up, please. Okay. If you need me to stop or go over again, I will. But we are almost there. We are basically there right now. I'm telling you the final approximation that we will be using throughout our electronics journey. So we will just choose two of this. That's what I'm saying. Which two? The pair of bands that will mark the boundary between where the electron is kind of stuck and cannot do anything and never participate in conduction. And we only care about conduction and non-conduction in electronics, right? And the band, whenever the electron gets to the band, it's kind of free. So it could be these two bands. It could be these two bands. We don't know. For different materials, it's different. Okay, so we'll see. We'll gradually see. And the reason why I told you this is because in the next slide, we're going to see just two lines of. This is the next slide. So in the next slide, we have, in this zone, we have two bands. This is one band. This is the other band. You might say, why is it so nice and rectangular and flat? Because we want to simplify it. For different material, the shape will be different. I mean, no point in trying to draw parabola or everything. Okay, so it's a band. It's a band of energy. You're just expressing that this is a band of energy. Does that make sense to you? You have a zone, a range of energy that's allowable, and you have another zone that's allowable, and in between, there is a forbidden band. That's exactly what this represents. So from now on, we'll be dealing with band diagram that will look as nice and flat as this one. But you know the origin of it. And you know, why are we looking at just two of them? There are more on top of it. We don't care, but because practically we're never going to use those unless you make it into plasma, like put it inside the sun or something, right? Making sense? So for all practical purposes, we are good to deal with just two bands that will interact essentially with each other. One of them, that's why we have to find names. Alice and Bob, for example, right? Because we always be dealing with two bands. Let's give them some name. We decided to give one of the bands that makes the electrons free, conduction band. Why? Because obviously when the electrons free, or electrons are almost free, they conduct electricity. So we decided to use the term conduction band. And the band right underneath that conduction band, which basically can supply electrons to the conduction band quite easily, is valence band. Basically, there's source of valence electrons, the electrons at the outermost shell. Does that make sense? So valence band and conduction band. This will keep coming back to us always. Now, take a look at a semiconductor, say silicon, at absolute zero temperature, which is hypothetical, for example. You have no free electron because it's perfectly silicon, 4 electrons paired up with 4 others. So no free electrons at all. But as you increase the temperature, some bonds start breaking spontaneously. So basically, maybe one of the bonds will break and an electron will become free. For some reason, no reason altogether. Just because you increase the temperature, the bond will break. Now, here is how we describe that incidence using a band diagram. So remember, these band diagrams in the y-axis, they represent energy. They represent energy, right? So the higher you go, the more energetic the things are. So can I describe it this way? That if I provide higher temperature, that is bringing in thermal energy, and just to quickly tell you, kT over Q is a measure of thermal energy. T stands for temperature in Kelvin. K is the Boltzmann constant. Q is the charge of electron. Okay, so that's how you calculate thermal energy that you bring into the system. So if you provide thermal energy to the electrons, they will go up and get to the other band. And you see, I'm only showing it will go up to the other band. I'm not saying it will go up and say somewhere in between. No, it's a forbidden band. Electrons cannot get into that band. Otherwise, it will. I don't want your energy because I cannot do anything with it. Make sense? It's never. It's going to be like a transparent thing to that energy. Will not absorb that energy at all. Okay, so that's how we explain the situation using band representation. And also, once an electron goes to the other zone, just take a look at this material. This is essentially a neutral material. Why? You have an electron, but that doesn't mean you have an extra electron. You have an electron that is moving around, but you also have a positive charge somewhere within the material that is representing a deficit of electron. So essentially, it's all even. It's a neutral material. Am I making sense? Simply because you have a free moving electron doesn't mean it's negatively charged. Just keep that in mind. So in energetic sense, you have a positive charge at the valence band. You have a negative charge at the conduction band. That's how we represent it, remember. So in total, the material is neutral. Positive charge, this will be more abrupt in the next slide. Let's go to the next slide. Let's see. So we are gonna take a better look at this band diagram now. Again, our famous EK diagram. EK diagram. You see, energy versus wave number. Okay. All right. Now let's see. This is a band, obviously conduction band, and this is valence band. And I told you we will be just looking at two bands from now on. Now we're looking at a more realistic, like parabolic shape, real band. I mean, it's not I who is deciding on which band to show. Is it flat or is it parabolic? These are all taken from the textbook, by the way. I decided to take sections from textbook as screenshots and put it there rather than going through, columns of text and making you completely demotivated. All right. Because the key points are quite simple, honestly. Notice there are some dots inside this zone. Do you see that dots? Is that visible to all of you? Blue dots. And here, there are also some dots that are empty. Like, these are filled, these are empty. These dots represents quantum states. And I told you that there will be tags. Remember we talked about tags? You can assign tags to different electrons. Primary quantum number, second N, L, M, and spin quantum number, right? Remember we talked about tags? So there are a limited number of tags available. So remember, just imagine that these dots are kind of like tags that you can assign to the electrons. So if you have 30 tags available, I would say in a more, engineering sense, you have 30 quantum states. Simple. Okay. So within an energy band, it's an allowed range, but within that range, you have quantized level that are available to the electrons to take up. It's not infinite. It's a finite range of energy. Okay. So you have quantum states. And when I say it's filled up, meaning all the electrons have taken up all the tags, no tags left. So it's completely full band. On the other hand, for the conduction band, these are all empty. So you have quantum states. These empty circles represent quantum state. So the quantum states are empty, meaning there are electrons can come in and take those states and claim those states. Oh, I'll take that tag. I'll take the other tag. So it's possible for the electrons to take the tag. Okay, first thing. So let me explain. This is 0 Kelvin. At absolute zero temperature, which is a hypothetical situation again, all the electrons will try to remain at the lowest possible level if there are enough quantum tags available. Remember, it's a big asterisk. If there is no tag available, then the electrons will have to go up. No option. But now, if you increase the temperature, some of these electrons will absorb energy and go up to the higher level. And notice that if you have 6 electrons moving to the other side, there will be 6 more quantum state filled up now. Others are still empty. Am I making sense, folks? Do you see that somehow? Okay. Okay. In a second, I'll try to explain how this simple EK diagram could be used to understand the concept of solar cell. Let's do that. Okay, let's see. Notice once you create some empty energy states, this was valence band. This is conduction band. Okay, let's talk about the conduction band first. Once you send some electrons to the conduction band, the electrons can then freely move around. So all on a sudden, you have created electrons within the same material that was previously not conducting at all. Within the same material, you have somehow created electrons that could flow around. Because in conduction band, electrons are kind of free to move around. Am I making sense? Okay. Similarly, there is another situation in the valence band. So you have some empty states. Now, the other electrons can gain some energy and come to these states instead of going all the way to the conduction band. You see? So there could be movement of these electrons within the valence band as well. It's possible to have some electron movement within the valence band as well. You see that? Now you have created that possibility. And one more question. I mean, again, I know it's difficult. You are learning and then trying to keep up and ask questions, but let me ask for you, because I'm sure at some point somebody will think about it. Why did we send the electrons only from this level, not from here? Because who is more probable to gain energy and get to the... So if you are trying to cross a bridge, you're already at the front row to cross the bridge, right? You will be the first one to cross the bridge, don't you think? So there is a bridge, and these electrons were already energetically high. They had slightly higher energy than the rest of them. So the moment the temperature starts increasing, they will be the first one to gain enough energy and jump. And do you think this electron will prefer getting to this point first and take up that other tag? If you're given an option to pick up any land, you'll take the land beside the lake first. And then when all the lands are taken, then you'll start moving inland, right? Don't you think? So similarly, electrons will definitely prefer the energetically best solution, best tag. Not all the tags are identical. Remember that. They have slightly more energy than the other. They're all good, but some are better. So the electrons will definitely take up the ones that are best, which are the less energetically, the ones that have less energy. All right. So let's move to the next slide. Here, we'll talk about a concept which we will keep encountering over and over again in almost every equation moving forward. It's called effective mass. It's actually a very simple concept. Let me explain that. Don't read the slide, okay? Just listen to me. Hopefully it will be clear and you don't even have to read it at home, honestly, if you listen to me clearly. So imagine an electron getting into a material, and material has atoms everywhere. And an electron trying to pass through, because you've provided some sort of electric field and it's letting the electrons flow through the material. So when you apply an electric field, it provides a force to the electron to try to flow through. It's called electromagnetic force, right? So when the electron is trying to flow through the material, all on a sudden, it will start interacting. It will be repelled by another atom or attracted by something. So it will keep interacting with the material itself. Don't you think? So there will be a zigzag motion. Instead of a really nice and smooth motion through vacuum, there will be a zigzag motion. So almost at every crystal site, there will be some sort of scattering event. So am I making sense? All right. So you guys remember Newton's famous equation, F equals ma, force equals mass times acceleration. That's a very simplistic equation. If you provide just one force on an object and it accelerates, you can easily calculate force, mass, acceleration. But what if there are multiple forces? One trying to push it this way, the other one trying to push it the other way, like all sorts of forces coming together to create an effective force, right? So what do you do then? You write the total force equals ma, not just one force. F1 jog F2, you see the point? F1 plus F2 plus F3 plus F4, not necessarily always plus, it's a vector. So basically what I mean by that is vector sum, right? So summation and effective force, the total effective force will be mass times acceleration. That's the final thing. However, once an electron is inside a material, can you calculate the force? You cannot. You only can calculate one force that you apply externally. But once the electron gets inside, the others are stochastic and random almost. You cannot calculate those individual forces. So how can you calculate? Oh, now it's working, looks like, is it? Yeah, okay, it's going back, but it's okay. Now it's working. Okay. My point is, once the electron is inside the material, you have an external force that you apply to the material, so to the electron, sorry. External force that you apply to the electron, but there will be an internal force. You cannot calculate the internal force. You cannot measure the internal force. It's impossible for us to do. However, people figured out a way to lump this internal force together, the effect of the internal force together, into the mass. And here's what I mean by that. And there is an analogy, by the way. You see, you can read it at home. I'm going to explain it. And also, I mentioned this. We must be careful not to take analogies too literally, okay? Just take it to help you understand. Imagine you have a golf ball, and that golf ball is, you just let it go, it's falling through air. You see that it's massive, it has mass. Which one is massive, more massive, a ping pong ball or a golf ball? Golf ball, right? You can, how do you know that? Based on our experience of how it interacts, we can easily understand this is massive, the other one is not. Looking at how fast it moves, we have some perception. So similarly, if you let the golf ball fall through water, all on a sudden it will be falling slower, don't you think? So it will be falling faster in air, but slower through water. Now, if for some reason you don't understand that there is water, there is air, you just see all on a sudden the same ball, same object is falling faster versus falling slower. You'll possibly consider that, oh, this is more massive, this is less massive, something like that. It will appear to you that, oh, this is not moving as fast because it's more massive, something like that. I know it's not real, and I told you that's the reason why I don't take it too seriously, because now, oh, if there is no barrier, all the objects with any mass will fall, as you know, gravity, right, will attract with the same force. So I'm not getting there, by the way. All I'm trying to show you is when there is more restraint, when the golf ball is trying to fall through water, there is more resistance. It appears that it's more massive, it's more heavy, it's not moving as fast. But through air, it's like, okay, really nice and fluid. All right. Similarly, when electrons flow through semiconductors, we don't use the rest mass of electron. You all probably know the rest mass of electron, 9.11 10 raised to minus 31 kilograms. But essentially, inside any material, not necessarily just semiconductor, in any material, effective mass will be used instead of the regular rest mass. Okay, because effectively, there will be internal forces that will interfere with the external force. So you will never get the mass. So if you just calculate F equals ma and basically use electron's mass, you can never correlate force with acceleration. They don't mean much because you will be missing one extra component of force. That's why we use a term called effective mass. So this effective mass basically just ignores the internal forces. All you deal with is external force, and you just assume that this particle, this object, is just more massive. Or I shouldn't say more massive, it could be less massive as well. Imagine if the forces are such that it's helping the object move faster, then the effective mass will be lower than the regular mass. Or if the mass is as such that it's moving slower than it should, then the effective mass will be more than the rest mass. So typically, let me just get to the next slide and show you what this is. A very commonly used terminology, which is not really physics based. It's based on practicality. We basically use it for practical purposes. Okay, there is no physical significance of effective mass. Electrons don't know that they have an effective mass, by the way. We just assign them as a mathematical tool. Do you now understand what effective mass is? All right. Another important thing, the concept of hole. In semiconductors, in any semiconductor device that you will ever use moving forward, diode, BJT, MOSFET, FinFET, whatever, you name it, okay? HEMT, everything will deal with two things, electrons and holes, okay? And I'll explain the concept of electrons and holes in this section. You'll all understand what electrons are, obviously. I don't have to explain that. But what is hole? What do we mean by that? let's get back to this diagram where we talked about how if you provide some energy, electrons will go from valence band to conduction band and they will take up some space. And these are electrons, they can flow around if you provide them some inspiration. By inspiration, I mean electric field. If you apply electric field, conduction band, they're free to go wherever they want to go. So they will flow around. But what happens to these electrons? Let's try to explain what happens there. If you provide some electric field, all those electrons, all on a sudden, will have a choice to get to a different location, to get a different quantum tag. So they can move around. Am I making sense? So these electrons can move around. But the point is, once, let me just zoom in. I'm sorry, I'm dealing with really bad technical difficulty today. So I hope we still can get through this as a team. So my point is, imagine this electron trying to get to this location and populate this empty quantum state. What will happen to the place it left behind? There will be a new empty quantum state there, don't you think? And other electrons can potentially fill in, and then there will be another empty state there. So apparently, as the electrons move around, it will be as if the empty states are moving around. Does that make sense to you, folks? Okay, try to visualize this one more time. When this electron gets to the top, it's as if the empty state came to lower energy. Similarly, when these electrons move to the top, it's as if this empty state will come down again. So apparently, the empty states will come down in energy, and the electrons will go up in energy when you provide external energy, don't you think? Can you visualize this, please? Okay. And there is another analogy, and don't take analogies too literally, but I hope it helps. It talks about, let's talk about what happens there. So once an electron breaks away from, it's not letting me know. Okay, yeah. Once an electron breaks free from a location, it gets to satisfy this empty broken bond. It will create another broken bond here, and then so on. So exactly the point I'm trying to make. Once the electrons move, they leave behind a new empty spot, and it could be visualized as if the empty spots are moving, not necessarily the electrons are moving. Does that make sense to you guys? Now, tell me something. Imagine for some reason, there are two empty spots. And that two empty spots will lead to movement of all, hundreds of electrons. They will all keep switching their places. Which one is easy? To track two empty spots and see where are these empty spots going? Or is it easy to track all the hundreds of electrons that are moving places? Which one is easy for you? Well, just go ahead and tell me. There's two empty spots, right? So that's exactly what we do. Engineers decided, because the math is difficult, to explain and track the properties of all those electrons that are moving places for no reason. It's easy for us to just track two empty spots or whatever empty spots we have, because typically their number is much lower than the electrons. So they just decided to make up a concept called holes. So instead of empty quantum state, it's like a mouthful, we decided to call them hole. And see, it's easy. So we treat it like a particle. It's like electron and hole. And why do we treat it like a particle that is exactly opposite to electron? Here is why. When electrons get energy, when electrons take energy, they go up. You see that? You provide more energy to electron, they will go up in the states. What happens to the empty spots? I just explained that, remember? When you provide more energy to the system, electrons will go up and take an empty spot. But the empty spot will go down and down in energy gradually. So it's as if, as you energize these particles, these holes go down in energy and electrons go up in energy as you provide more energy externally. Does that make sense to you? So can we visualize this in a way that is like exactly opposite to an electron? Whatever the electron does, it does the opposite. Are you guys all with me so far? And also, a hole represents an electron deficit in a place. So we could treat it like a positive charge particle. Electron deficit is positive charge, right? That's how we treat it. So holes are treated as positively charged dummy particle. They don't even exist, but we just make up that concept that hole exists. It is what it is. Engineers decided to do so 60 years ago, and we are living through it. And textbooks will make it in a way that you start believing that there is actually a particle called hole, right? Because it's so ubiquitous. It's everywhere, everywhere. All right. So now you understand the concept of hole, I hope. And the more you read, more you go through the lectures, hopefully more sense it will make. And you'll see how useful this concept is. Honestly, it has been a lifesaver in terms of math and analysis to consider holes instead of electron. And whatever I just explained to you, that exact same thing has been illustrated here. So instead of dealing with all those electrons that move around to respond to these empty spaces, people decided to just consider as if you have some positive particle somewhere, right? And treat that no electrons. We don't care about the electrons. No electrons. We just have positive charges, holes, and they will move around. That's a conceptual, understanding of hole. All right. So let's move to the next slide. Where is the next slide? This is the next slide. So now, based on the concept of band theory that we just have learned, and we have seen the origin of band theory, let's try to explain the difference between metal, insulator, and semiconductor. And hopefully it will make a lot of sense now. We understand what quantum states are. We understand what energy bands are. Do you understand what quantum states are? In simple words, they are quantum tags that you can assign to electrons. There is limited supply. Basically, they only make, say, 100 of them. Say, there is a limited number of quantum tags available in every quantum band, in every energy band, every energy band. And there are bands of energy, meaning ranges of energies that are allowed. Ranges of energy that are not allowed. It's called forbidden band. So let's see. Take a look at this diagram. Here, these parallel lines represent a band. So this is a band of energy. The band of energy. And all these tiny small ruled lines, they represent quantum states within the energy. Okay? They represent quantum states. And see, some of the quantum states are filled with electron, and some, the gray, light gray, represents empty. So they basically some are full, some are empty. So within a band, you could have some energy states taken up, some energy states empty. And using common sense, we know the ones that are taken up will always be in the lower energy first, and then higher energy. All right. Similarly, this is an energy band that is almost full. And again, these are all taken from the textbook. So you could revise that there as well. This is an energy band which is almost empty. This is an energy band which is almost full. You see why? Because these blue dots that you see, these blue dots, they represent electrons. So electrons have taken up the space, the quantum states already, except a few. So that's why it's almost full. Now, considering these two cases, let's see a material where you have a valence band and you have a conduction band. Haven't we seen that before? Valence band, conduction band. What is there? In between, you have a forbidden band. And by the way, forbidden band is represented as a band gap. E.g., G stands for gap. G stands for gap. So you often mention this as a gap energy, a gap between valence and conduction band, or band gap. Remember, this is how impactful it is. Band gap is the signature of a material. Band gap. So basically, we could figure out through a spectroscopy whether in a sample you have silicon or carbon or copper or germanium, what do you have, based on band gap measurement. So basically, band gap determines the amount of energy a material absorbs. And then you could back calculate and figure out. Silicon has a signature band gap, 1.1 electron volt. There are other entities with a specific band gap. We use the band gap to represent a material. Does that make sense, folks? All right, it's a signature. Now, moving to this one, we are going to look at a semiconductor. So in a semiconductor, in a regular sense, all of the states, quantum states in the valence band are full. All of the states in the in the conduction band are empty. So nothing happens, nothing moves. But remember, that's at absolutely zero temperature. But when you have a slightly higher temperature, electrons will gain energy. You don't even have to apply a voltage. Simply because of thermal energy, electrons will gain energy and get to the upper level, conduction band. So now, by the way, simply because electrons have gone to the conduction band, does that mean they will start moving? Here is a huge misconception that many students have in their mind. And let me try to clarify that. When I say electrons will go from valence band to conduction band, does that mean they will go from one place to the other? Are you visualizing this in a way that silicon has different layers, upstairs, downstairs, electrons will go from downstairs to upstairs? No. What is in the y-axis, folks? Energy. Think of energy like money. Me and my buddy, we could be sitting side by side. My buddy could have more money. So he basically is in the conduction band already, right? He has more money, meaning more energy. I have less money, I'm in valence band. But we are physically in the same place. Simply because an electron has more energy and has a higher quantum tag, doesn't mean they will have to be physically in two different locations. They could be physically in the same crystal simultaneously, but some electrons are ready to conduct and some electrons are stuck. But they could be physically in the same material at the same time. Does that make sense, folks? Don't visualize it like different levels, actual physical levels. This is a graph. Remember, it started from EK diagram. This is a diagram, X versus Y graph. So as you go higher up in energy, and you see we are basically dropping the X-axis. We don't care about K anymore. We just care about energy. We are simplifying our job. As we move forward in these lectures, we'll drop a lot of physics. We'll keep dropping physics. That's why physicists will hate engineers, actually, because they do all those hard work, do blah, 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 blah. And then you ignore everything, just keep the energy. Anyways, but it is what it is. We make things work. I mean, look at the bright side. We probably try to see beyond math and do something with it. The point is, so simply because I said that electrons will take energy and get to the conduction band doesn't mean they will have to migrate and get to a different location. They'll just be ready. Now I have more energy. It's like, okay, making sense? All right. Now, why did I emphasize that? Because in a semiconductor, when you heat up, you don't even have to heat it up. Like if you keep it at room temperature, it's already non-zero. Anything that is not zero will have some thermal energy. And some electron, no matter how few, will get to the conduction band. And they will be ready. They will not conduct. Remember, they will be ready to conduct. Because they have enough energy to just break free from silicon and go somewhere. When will they conduct? When? Only when you apply an external electric field. That's a different scenario. Now, this situation where electrons are ready to conduct, they are in the conduction band, it's called thermal equilibrium. Remember that, thermal equilibrium. So temperature has created a situation where they are okay and ready to conduct, but they're not conducting. So they are in an equilibrium. It's called thermal equilibrium. And whenever you apply some sort of external stimuli, it could be electric field, and that's not the only thing. It could be magnetic field as well. It could be light, enough energy, blah, blah, blah. It could be something else, some sort of energy that you provide to the electrons to move them from one place to the other. Electrons can start moving because they're free now. Which electrons? The ones in the conduction band. And don't, by the way, you might see, oh, we have just created that many electrons for conduction. Remember, we have another indirect participant. All those empty spots right here in the valence band, what will they lead to? Indirect electron movement here. What we want to avoid, by the way. We don't want to explain in terms of electrons. What do we do? Explain in terms of holes. So what I want to do is, let me do this and zoom in here. Just want to clearly show you. Okay, so these are electrons. The red ones are electrons. And we visualize it in a way that these are, I'm just trying to make a different shape and it's not letting me do it. Like square. So as if these are holes. So you have electron hole. That's exactly how the engineers talk about things. We generate electron hole pairs because they are always created in a pair. Once an electron goes from valence to conduction, you create one hole and you create an electron pole. That's how we are going to put things together. Making sense? Right. And remember, if and when you go for interviews in like semiconductor company, any company, they will try to ask simple questions. And I've seen that with many students. Like they will ask you simple questions. They'll try to see whether you really understand the basics. Because the higher level stuff, they don't expect you to know because they will train you up for 6 months when you join. There are many trade secrets that they're not going to openly publish and whatnot. But they don't want that. They just want you to know the basics. So this type of simple minor basics are often missed by the students. So I'm trying to hopefully provide you the basic understanding of the overall semiconductors. Anyways, so let's get back to this one. So we understand what. Oh, so this is what a semiconductor looks like. All right. So let's get to the next slide. I meant to get to the other next slide, this one, and show you how an insulator looks like. Oh, this is for metal. Insulator will come later. Okay, let's start with metal. So in a metal, there could be two situations. Number one, let's start with this. You have a valence band that is completely full. Remember that there is a difference. So you have so many electrons that the electrons have taken up all the available quantum tags. So there is no way for the remaining electrons to stay in valence band. They have to stay in the conduction band. There is no way they can come down. Just the nature of the material. So you have conduction band that is already partially filled to begin with. Naturally, it's partially filled. So these electrons are ready. They were born to conduct, basically. You see that? So that's why metals are natural conductors. You don't have to dope them. You don't have to do anything. They're always conducting. Are you all good? Semiconductors are like, they have to have some motivation. Should I conduct? Should I go to the, okay, you are telling me, okay, I'll go. Like you have to do something to them. Even then there is a few electrons that will go because of thermal driven process, and then they will conduct unless you do something. And I'll show you what that thing is. Doping. I told you already, doping. We haven't seen doped semiconductors yet. We haven't seen how the band diagram looks like once you dope. That's an interesting thing. And band diagram will help you explain what happens when you dope a semiconductor in a few slides. But for a metal, it's natural. You have electrons that are naturally in the conduction band, ready to conduct. There is another situation here. There are some materials, and this is purely from math, by the way. There is something called density functional theory. You could do those calculations, DFT analysis, and you could basically calculate the band diagram for almost any material. And we do that in our group as well. Apparently, for some materials, it appears so that the conduction band and valence band will overlap. So there is no forbidden band. So the forbidden band exists because we didn't have any mathematical solution. So we just made it forbidden. Okay, it's forbidden. That you cannot have it. But what if for some materials, mathematically, you see a continuous situation where there is no forbidden, no, inaccessible zone? Then you understand that the valence band and conduction band have overlaps. Okay, so no forbidden band. So any electron that is available here could also be available for conduction. So they're kind of like volunteers. I mean, whenever you need me to conduct, sure, I'll go and conduct. So they are also metal. So basically, in both situations, you have ready electrons that are always available for conduction. That's why there some metals are like this, and some metals have band gap. But even with band gap, you have enough electrons in the conduction band that they conduct. Right? Typically, these are the best quality metal, like no band gap at all. But here, they are also very good. Anyways, let's move to the next slide. And just in a second, just to get back, in an insulator, the only thing will change in this diagram. Can anybody tell me what will change in this diagram for an insulator? The forbidden band will be bigger, exactly. So to give you some number to calibrate you, for silicon, band gap is 1.1 electron volt. For oxides or other insulators, it could be 9 electron volt. So like almost 9 times, 10 times, okay? So you see, huge gap. So it's very difficult for thermionic process to excite electrons to get to the conduction band. So they don't conduct. All right, so let me get to this point and see, this is basically the second last slide of this lecture. So we're almost there. You have survived through this thing. The next lecture, I have already uploaded them, by the way. I hope remember to make it public. You'll see the title change. It's no longer quantum mechanics. It's part 1, part 2, part 3, all the parts are done. It's going to be semiconductor in equilibrium. Okay, so we have gone into, I feel bad. I feel good now because I was a little bit nervous. This is probably the situation where you lose most of the students. In a way, you may not drop the course, but you lose interest. And that's a kind of worst kind of sign off. Like, okay, I don't care. I just want to pass this course and get out. You see, and I have graphics. Maybe I'll show you in one of my classes. Like what happened over the last 25 years in semiconductor industry. Who was the leader? Who became the leader? And who is the leader now? So there is always a dynamics, right? It's not a rigid, like I'm always going to win. So it's like the Olympics. Like if you prepare the best, I mean, you have a better shot. It's not like this country is always going to get the gold medal all the time. Okay. So similarly, unfortunately, US semiconductor industry is struggling, as you can imagine, or if you follow the news, if you read some articles here, you don't have to look for research articles, just look for articles in conventional newspapers. Why do you think the semiconductor industry in the US is struggling? I mean, they're the ones who invented this chip design thing, right? And now they're struggling. Why is that? Simply because these things were not really fun to begin with. And many students like you, honestly, these are not robots that move around that you can see, wow, look, it's a walking robot. Line follower, it's a drone that's flying around. You can take photos and whatnot. They're not really stuff that you could interact with. These are all theoretical maths, blah, 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 blah. Okay. Remember, you need engineers as well as scientists. If you just do science and don't do engineering, you will fall behind because there's a lot of engineering challenges that you have to overcome. And vice versa. You cannot live without scientists because otherwise we have no idea what's going on there, right? So somebody checked out like, okay, I don't care. If I have to go through this math, I would have taken physics. I mean, I don't care. I'll just go do robotics, machine learning, whatever, right? And then there was a generation, actually a couple of generations who checked out and didn't care about it. And you cannot fill up brain deficit with money. Like no matter how many hundreds of billions of dollars you invest, you have to go through the tough process of creating workforce or basically brain force to actually do the work or think about stuff. Anyway, so I really want that to change. Maybe some of you, maybe not all of you, but at least many of you will hopefully, volunteer to be in this domain. All right, getting to the point. So remember chronic penny model. I'm going to quickly give you the answer here. I don't want to, overhype it. In the very first lecture, we started with crystal direction, 110, 111, blah, blah, blah. Remember that thing? I showed you different directions in crystal. And I told you that different directions have different purpose and different directions have different utility in semiconductor industry. That's how we learn to identify them. Is it 111? Is it 100? Is it 110? We could identify different planes. And here is why that is important. Let me tell you. Chronic penny model that we just dealt with had a periodic potential. And in the equations that you got, there was A and B. I don't want to go back, it's too much work. But if you go back home and take a look at those equations, there was A and B. What is A, what is B? Can anybody tell me? If this is A, the other thing is B. So basically, these represents the crystal structure. How far out are the atoms? How much space will each atom take? So A and B represent that. Does that make sense to you? So notice, in a crystal, if you go along this direction versus the other direction, you see, if this is A, this is B, this is A, this is B. Is it the same across the diagonal? Is it the same across here? No. Even if it is repetitive, it is periodic, but the spacing A and B will change across different directions of the crystal. So the results, the band diagram itself, how did the bands come? Through those mathematical calculations that started with the periodicity, A and B. So if A and B changes, your entire band structure will basically change. So the same material can have different kind of band behavior across different directions. So you find the one that you like the most, and there are bases of liking or disliking, and you deal with that. So for semiconductors, these directions matter. Does that make sense to you, all of you? All right. So the last slide of this lecture is this one. So I'm going to show you this. This is gallium arsenide. This is silicon. Silicon, gallium arsenide. The two prominent semiconductor materials, okay? And remember, EK diagrams, I don't want to go back again. They are symmetric in both direction, positive and negative. So basically, if you draw it, it's going to be like this. Am I making any sense at all, folks? It's symmetric in terms of positive and negative K. All the EK diagrams are symmetric. Just go back and see the slides. So people decided, hey, why are we just drawing the same thing twice? Let's do one thing. Since two directions matter the most for semiconductors, one is 111, one is 100. These two directions matter the most. Okay, people tried the others and they failed. And they said, okay, we just deal with these two. So they draw half of 100 and the other half for 111. Does that make sense? So basically, you are looking at two EK diagrams simultaneously. One for 11, and we just only draw the half. There is other half on the other side. Just remember that. Similarly, this portion represents 111. Okay, that's how the EK diagrams are drawn. Now, looking at gallium arsenide as silicon, you see gallium arsenide, there is a minima. This is how the band diagram looks like. Electrons will always try to stay close to minima. And there is a maxima here. Okay, will you give me like 1 more minute today? I just want to finish this. I want to just, thank you. Sorry. So I'll take 1 extra minute. We're at 44. So this is how the band diagram for gallium arsenide looks like. And this is how it looks like for silicon. What is the difference? The minima here is a little bit, in a strange position, not exactly aligned with each other. So turns out for optoelectronic applications like diode design, electrons, once you excite them and put them to conduction band, they can always come back and lose that energy. They can give up that energy, okay? And they can come back and recombine. So typically, it's easy for them to come back if there is a situation like this, and you get the most out of it. You get light as an energy when the electrons come back and recombine with hole. Electron hole coming back, electron will give out the energy it had as light. Most efficient whenever they are aligned, perfectly aligned. To peak and valley is perfectly aligned. But if you have a situation where the valley and peak are not perfectly aligned, first the electrons will dissipate some energy as heat. We call it phonon. Phonon is nothing but a very simplistic term, heat. So it will dissipate some energy as phonon and some energy as photon. So we love photon because we're trying to create a diode, say. But in the process, it will lose a part of energy trying to match up and then come back to this point. Making sense? Do you think the electrons will jump from here to there? No, it will first come here, basically. So while trying to come here, they will lose some energy laterally as phonon, and whatever vertical will be lost as photon. So they will be less efficient. Making sense? So which one of these two materials will you use to make diodes, silicon or gallium arsenide? There you go. A band diagram helps you decide to pick a material for optoelectronics versus conventional electronics. So apparently gallium arsenide is a better material than silicon in some sense. But we also like to have that security of electrons not randomly coming and recombining, because you don't want your iPhone to work as an LED all the time, right? Anyways, so there are reasons. So this is the last slide. And this is called direct bandgap semiconductor, where they are perfectly aligned. This is called indirect bandgap semiconductor. So silicon is an indirect bandgap semiconductor. Doesn't matter. It's okay. All right. So we're done with this. From next slide on next lecture onward, we'll start with semiconductors in equilibrium. Thank you so much.